So actually, what I'm about to show is very much in response of the previous talk. I mean, in the idea of the previous talk. So I work with Paul Goldbart. We do statistical mechanics, which is kind of the stupid version of nonlinear dynamics, where we don't look at the dynamics, we look at the ensemble averages. But so I'm going to be talking about a problem which has a very simple reduction in statistical mechanics, but is still very much an open problem in nonlinear dynamics because it has very much chaotic behavior. But this is in the realm of protein physics. And it's based off of a paper which I'm writing right now. So a protein is this collection of molecules, and you can look at the shape of the protein, which is governed by some sort of very mountainous energy landscape. So on this axis, I'm going to draw a coordinate which I'll call shape. So part of the reason why I'm doing a chalkboard presentation is I don't have any pictures for this because I don't do any numerics. And this one is going to be called energy. So a protein is continuously bombarded by water molecules, but it also consists of these atomic bonds which form this energy landscape. And essentially the dynamics are controlled by taking variations of the energy with respect to the shape, which I'll call U for now. Now, if the protein is kept in water, it's going to have some sort of dissipative dynamics. So we're going to say that it doesn't contain that the shape evolution does not contain any inertial term. Instead, contains just this dissipative term with a constant that controls the dissipation. And there's a minus sign out in front. We should recognize that from forces equal to mass times acceleration, except without any acceleration. So if we were to place the protein, I'll denote by this point in shape space, it'll eventually kind of fall down these hills and go back and forth for a while, but may come to rest at some local minimum. Now, like I said before, the protein is continuously being bombarded by water molecules, so it picks up some stochastic behavior, which will actually cause this trajectory to be non-deterministic, but rather spread out. So there's a random walk associated that goes along with this trajectory, kind of sending back and forth. And we'll describe this diffusive, the stochastic behavior, by a contribution I'll call C to this equation, where the on average C is going to be 0, but it has a non-zero standard deviation. So actually, let me write it out in full glory. So it's going to be a function of position and time, where position is somewhere inside the protein. It's going to be, the standard deviation is going to be governed by a diffusion constant, and then it's going to be white noise, so that the noise is uncorrelated. And then there's all the functions for position and time. So essentially, due to this noise, if a protein, sorry, I'm throwing chalk around, if a protein settles in some sort of metastable state, eventually the noise will kick it out, probably, and drive it to an absolute minimum state. Whoops. So protein function is typically governed by its shape. For example, if you think of molecular motors, the molecular motors bind to something, and then whatever it binds to changes the shape of the protein, and then it proceeds from then on. So we're going to call that process allosteric regulation. So we have a protein. I'm going to denote by a blob because I don't know how to draw proteins. And this blob may change shape once some other molecule binds to it, which induces a change in the blob shape, and now it works in some different way. What that corresponds to is changing what the minimum of the free energy landscape is. So if the protein is resting around some free energy minimum, we'll call that a relative equilibrium of the dynamics. And essentially what happens is the attachment of some regulator molecule will change the relative equilibrium that the protein is sitting in. Now, my work is concerned with a different version of regulation in which the attachment of a regulator molecule does not change the overall protein shape, but rather changes its dynamics. It changes its Brownian motion about a static mean shape. So not this, but rather the addition of this molecule keeps the protein in its energy minimum, and the protein is fluctuating about this energy minimum. But the addition of the molecule kind of broadens, changes the shape of the energy minimum, thus changing how the protein fluctuates about it. And then this change in fluctuations of the protein shape about a static mean shape then changes how the protein behaves. And so this kind of goes back to the linear response idea, is that in a very sort of abstract sense, the perturbation is a small shape change to the protein, a small addition to the protein shape, which then changes the protein's dynamics about its equilibrium state. Now, how much time do I have?
10 minutes.
About 10 minutes left? Okay, good. So what we're going to be looking at is, now I'm going to draw a different version of space, in which the protein has a mean position, which I'll denote by P, which is the protein's mean shape. And then this diffusive dynamics drives the protein's shape in a random walk around about this mean shape. But it's a random walk with that costs some energy. And if the protein is sitting at the bottom of a well, to linear order, that energy is going to be quadratic about the protein's displacement. So in fact, this is a random walk that costs some energy to move. So in order to look at this, we're going to look at dynamics about the bottom of this energy well, and linearize the problem, linearize the dynamics about this energy minimum. So I'm going to draw an effective parabola describing the energy. And that parabola is going to be quadratic in the displacement field. So the energy is going to be some constant, which is actually a tensor, which is quadratic in the displacement field, describing the deviations of the protein from its mean shape. So this displacement field roughly describes the deviation of the protein shape from its mean shape. And this energy is the energy associated with linear elasticity. So, so proteins are actually composed of, a large number of molecules. Right now, we're treating the protein as a continuous object, as a continuous elastic object. So if we go back to this dynamical equation describing how the protein shape evolves, taking the derivative of the energy with respect to the displacement field gives us a new equation. Note that these displacements are vector quantities. We're dealing with proteins in 3 dimensions, so they have displacements along x direction, y direction, z direction, and all that stuff. So the displacement field is going to be equal to Cij k L. Don't worry about all the indices. This is just a fancy form of Hooke's law. And then we have our noise term. So I'll show why this is essentially a ball and spring type of system in a second. So we can decompose this equation into eigenmodes corresponding to the elastic modes of the protein. So let's say that we've solved the eigen problem. Cij. So this is going to govern the nth eigenmodes. Just like you would see in quantum mechanics. This is a very similar problem. Then we can write the displacement field U as a sum of components, Cn of t, multiplied by these eigenmodes, which depend on position. And then we can use these eigenmodes to project this dynamical equation into its eigenbasis.
Do you assume elasticity tensor is isotropic, or you really use anisotropic?
Yeah. So in the end, really for a protein in this continuum description, it should be isotropic. But I'm going to leave the elasticity tensor the way it is, just as a shorthand. And all of these calculations work for general anisotropic elasticity, but not inhomogeneous. That requires some more work. So I'm just going to project these displacements onto their constituent modes, and you get a Langevin equation. So there's energy eigenvalues. And then you have to project this noise onto these different eigenmodes, but that'll just introduce another stochastic term that is more commonly seen in the Langevin equation. So what we have here is a system of, is really an infinite system in the continuum sense, but realistically there's a cutoff. A decoupled system of linear Langevin equations. So great. So we see that in this setting we don't have a nonlinear problem. And in fact, I'm kind of burying up some interesting chaotic dynamics that has to do with finding the vibrational modes of the protein in the first place, but we're just going to assume this to begin with. So by breaking the protein's motion down into its eigenmodes, we can now assign a nice basis to the shape space corresponding to the eigendirections. So I'll call this one psi 0, psi 1, psi 52. For all practical reasons, this basis is countably infinite. But the origin is going to correspond to the protein's mean shape, and then there's going to be a random walk through this huge space. But in order to measure the size of the Brownian motion, 1 minute left? Okay. In order to measure the size of the Brownian motion, well, in a normal random walk setting, we would measure the mean squared displacement of the walker from its origin, right? Well, this is going to be a Brownian motion, a random walk coupled to some sort of restoring spring. So if you like, we have our drunk that's walking around on the sidewalk but attached to a tether that kind of stretches and pulls him back. So there's actually going to be, in each of these directions, a finite mean squared displacement, which gives us the description of fluctuations as a sort of ellipsoid in this large dimensional space. That gives us a nice description of the protein's motion throughout shape space. Now, the attachment of the ligand is going to change the way the protein vibrates. Is going to change its eigenmodes. So this is where Mark Kack comes back in. You can assign geometric dependence of the eigenmodes. You can assign a dependence of the eigenmodes on the protein shape. Now, that's going to give a different basis to state space, which I'll call the primed coordinates. 50. And a slightly different ellipse describing the protein's motion. So in order to figure out the effect that this attached ligand has on the protein's dynamics, we have to compare these two hyperellipsoids to each other. And there is a way of doing this. It's called Adamar's variational formula. That is a classical result for potential theory. Now, we derived an analogous result for elasticity, but one thing that you have to keep in mind is that the radius is set by 1 over the corresponding spring constant. But if the protein has, this is where symmetry comes in, if the protein has translational and rotational degrees of freedom, that's going to have a spring constant of 0. So we actually have to take a slice that's orthogonal to whatever direction those translational and rotational degrees of freedom are. And I'll call that psi 0. Is going to be the direction of the normal modes. So we actually have to do this computation in a slice of this space and then compare the slices to one another. So right now I'm trying to understand, just as a summary, I have a formula that I derived using ergodicity, essentially statistical mechanics, that is able to compare the ellipsoids on these two slices that are created using zero modes. Now I want to understand how that translates to the chaotic motion of ringing within an arbitrarily shaped elastic body, such as a potato, and how that ringing changes upon the addition of a small foreign object. Thank you.
Okay.